Hi, welcome to Chemistry Unit 2. Today we're talking about EcBc and drawings and models. So let's review 2.1 and 2.2. These are questions that you should be able to answer and ask yourself as you do these problems. So its name is what name goes with it. Normally you're given the atomic number or the symbol. How many protons does it have? What is the atomic number? How many neutrons? What is the atomic mass minus the atomic number? How many electrons? What is the atomic number? What is the number of protons? What location is it in? Its group and period, meaning what column and what row. What category is it in? The chemical state of matter of one of three subcategories. And then what is its dot diagram? That's the symbol with its valence as dots. So as a review, you're given SI 2814. So you have to be able to do what is its name, protons, neutrons, electrons, group, period, category, and dot. So its name is silicon. There are 14 protons because it's the bottom left number. There are 14 neutrons because the 28 minus 14 is 14. And there are 14 electrons because, again, bottom left number. Silicon is in group 14 on your periodic table in period 3, and it is classified or categorized as a metalloid. The dot diagram would be Si with 4 dots, 2 on either side or 2 on the top, 2 on a side. Either way is fine. So drawings and diagrams. EC stands for the electron configuration, and it is based on the number of electrons. B is the Bohr model. It's a circular diagram of protons, neutrons, and electrons, but we will actually do a condensed Bohr model. That's where the BC comes in, condensed Bohr model. It is based on the total number of subatomic particles in location. So let's start with the electron configuration. The electron configuration is the placement of the electrons in shells and sections or orbits around the nucleus. Each shell contains a different number of electrons, and the following table might be helpful. On shell 1, it has one subsection of S, and there are only 2 electrons on shell 1. Shell 2 has 2 sections, S and P, with a total of 8. And you'll notice the totals on the far right-hand side tell you that the S section will only hold 2, the P section holds 6, the D section holds 10, and the F section holds 14. So shell 1 has 2, shell 2 has 8, shell 3 has 18, and shell 4 has a total of 32 electrons that it will hold. So the shells also jump. The period numbers are the shell numbers, and you've labeled those down the left or right-hand side of your periodic table 1 through 6. But there is a shell jump between the 4S and 3D, and then back to 4P. So right here, in between elements 20 and 21, put a 3, 38 and 39, put a 4, and 56 and 71, put a 5. There's a special jump there. On the other end of that section, put a 4, 5, and 6. Those are labeled on the big periodic table in the room. To do the electron configuration, you first have to find the number of electrons in level 1. Then you begin placing electrons into shells and sublevels following a chart on the back of your assignment sheet. You're going to record the number of electrons placed in the format shell sublevel number. For example, 1s2 means that there are 2 electrons on shell 1 in sublevel or section S. I'm also going to show you how to do this on the periodic table itself. So if you look at your periodic table, one of the things that you will want to do is the first 2 columns are the S section. Columns or groups 3 through 12 are the D section, and groups 13 through 18 are the P section. And literally, you are filling the electron configuration from the top. Now you'll notice that helium has jumped over here to play next to hydrogen because helium is actually part of the S section. So I'm going to walk you through the electron configuration for, say, beryllium. Beryllium is located right here. It is on shell 2 in the S block in seat number 2, like it was a stadium or a restaurant. So to write the electron configuration for beryllium, we would write 1s2, 2s2, because shell 1, section S, has 2 electrons in it, and shell 2, section S, has 2. Now, the smaller they are, sometimes the harder they are to see. So let's jump over and look at silicon, the example we had before. It's located right here on shell 3, right, in the P section, but we have to fill everything in front of it. So we would write down and fill 1s2, 2s2, 2p6, 3s2, 3p2, because silicon is in the second seat on shell 3 in the P block. One more, vanadium. Vanadium, we would fill 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then you jump to 3d, 1, 2, 3. Vanadium ends in 3d3. This is known as an electron configuration chart, and it tells you where to go and how to do this. And we do this, we call it the EC math. And you use this flow chart. So phosphorus has 15 electrons. So we would start with those 15 and say, shell 1, section S, right here, because this is where you start, 1s gets 2, because it tells you how many it gets. And now I have 13 electrons to place. And then you follow the arrows. 2s gets 2, and now you have 11. Follow the arrows. 2p can hold 6. Follow and subtract. Now you have 5. 3s can hold 2. Follow the arrows. You have 3 left. 3p can hold 6, but you only need to put 3 there because that's all you have left. And your goal is to end with 0. Then the electron configuration is hidden inside the math. 1s2, 2s2, 2p6, 3s2, 3p3 is the answer. We also have noble gas electron configuration. Sometimes, especially for larger elements, a noble gas electron configuration is used. This is where you use the closest noble gas as a reference and then continue the regular electron configuration. For example, element number 15, that is phosphorus, could be listed as neon, Ne, 3s2, 3p3. Let me go back a couple slides and show you what I mean by that. If neon is here and I want to go to phosphorus, I know that phosphorus is in 3p3. So I can go and do neon 3s2, 3p3. If something is on shell 4, I can use argon as its reference and then keep going. I don't have to write everything every time. If something is on shell 5, I use krypton as its reference and then keep going. We'll practice more in class. The next thing you get to do is the Bohr model. And a Bohr model has protons and neutrons located in the nucleus and electrons placed on the shells around the outside, and it's based on the electron configuration. Well, shell 1 will only hold 2. Shell 2 can hold 2 in the S section and 6 in the P section. So you notice this particular Bohr model has an S section, and it has a P section, and it has a D section. But not everything will. This is what normal Bohr models look like. And here in this bottom one, you can see there's a slight color change. The S section are blue, the P section that they color are green. But this one doesn't. It just has 2 on shell 1, 8 on shell 2, 3 on shell 3 for aluminum. Okay, so not all Bohr models are exactly the same. To help with that, we are going to draw a condensed Bohr model. Okay, so you might want a Bohr model as a template. Label the rings from the inside out. The P section holds 6, the S section holds 2, the D section holds 10, just like your periodic table. But this is what a condensed Bohr model looks like. A condensed Bohr model is just a shorter way of drawing a Bohr model that has the same information. It contains the total number of protons and neutrons in the nucleus and the total number of electrons on each shell or loop. So we start with protons and neutrons in the nucleus. We label the shells 1 through 4 or 5 if you need more towards the away from the nucleus. And we put the total number of protons, neutrons, and electrons on the bottom of each shell. Now, if you're not going to draw it or use a drawing in a Google Doc, you can literally list it as number of protons, number of neutrons, and then the shell numbers 2, 8, 3, whatever the case may be for what your element is. So here's an example of that phosphorus with 15. I went and got a Bohr model that I looked up online. I did the electron configuration, the complete one, not the noble gas configuration, but 1s2, 2s2, 2p6, 3s2, 3p3. And then the loop diagram, right, or the condensed Bohr model, sorry, name change. The condensed Bohr model has 15 protons, 16 neutrons. Shell 1 would have 2 electrons, right? And you see those down here on shell 1. Shell 2 has 2, 4, 6, and 8. And shell 3 has 2, 3, 4, and 5. That's the condensed Bohr model for phosphorus. You're going to be doing lots in class. Thanks for watching.